Okay. Well, hello everyone, and thank you for this opportunity. I think it's been quite a fascinating week to hear about all the theory and simulations, and I'm an experimentalist, so I'll be talking about some collective effects in the superlattices of perovskite nanocrystals. And okay, so two central questions that I hope to discuss is why superlattices of perovskites are special, because they attract a lot of attention, and then where does superfluorescence come from? I'll explain what it is. And I think I have an answer to the first question, but not sure about the second. So to give a brief introduction, so a very brief history of colloidal semiconductor nanocrystals. It started in the 80s with the works of Louis Bruce, who observed quantum confinement effects in the colloids of semiconductor nanoparticles when he was trying to sensitize like electrodes for photocurrent measurements. In the next few decades, there's been an enormous progress, which many of you witnessed and been part of. And over this time, basically impressive size control has been achieved over nanocrystals. Then their optical properties got improved, and all this excitement has been driven by an idea that the future of these materials is in the use of quantum phenomena. So nanocrystals are artificial atoms, and that's why we maybe can make some useful devices out of them. And nowadays, for example, you can go to the store and buy QLED TV based on indium phosphide nanoparticles or some cadmium-based ones, but we're not quite there yet in terms of making quantum computers and such. And one reason is that the most studied material, 2,6 semiconductors, suffer from defects which introduce non-radiative recombination channels. For example, you can make core shell particles with high quantum yield, but there always will be some defects that will quench emission and kind of prevent the use of these materials in quantum technologies. So the situation has drastically changed in around 2015 when community shifted their attention to the perovskite nanocrystals. And for instance, just 3 years after high quality nanoparticles of perovskites were prepared, superfluorescence being reported, which is a remarkable quantum phenomenon. So what are these lead halide perovskite nanocrystals and why are they special? So typically, I'll be talking about cesium lead bromide, which is prepared in form of nanocubes. Here's an example of the structure of this perovskite. So you have a lead bromide 6 octahedra interconnected in three-dimensional networks with the vacancies in between filled by a cesium atom in this case. It can be methylammonium or other monovalent cation. And when you make them of sufficiently high quality, you see this nice absorption spectra, which you can describe, for example, by assigning it a particle in a sphere-like electronic states. So why these materials are better or different from cadmium selenide, for example? So two main reasons, I believe. One is their peculiar electronic structure, which changes depending on the symmetry of the lattice, and there is a debate going on what is the lowest energy state. But it seems like the community is converging that the lowest energy state is a dark state, and then the relaxation from the higher lying bright state is for some reason inhibited perhaps by multi-phonon processes. That's what makes them, that's one thing which makes them very efficient emitters, especially at low temperature. And the second reason is polarons. These are ionic semiconductors, they're not covalent semiconductors, so when you form an exciton, electron hole pair, it polarizes its environment, and this sort of protects it from defects. And that's the reason why thin film perovskites have very long exciton diffusion lengths, and you can make efficient solar cells. So now from nanocrystals to superlattices. So nanocrystals are crystals made of atoms, and then we look at nanocrystals now as artificial atoms in the sense that we can build crystals out of them. So just, for example, by solvent evaporation, from the uniform nanocubes, one can form these microscopic, also square-shaped superlattices. So each of these squares is a assembled nanocubes of about 10 nanometers. So here's a few examples of the early superlattices. So in 2015, for example, Sargent group just centrifuged particles onto the solid substrate and obtained close packed films. And then several groups were seeing these superlattices simply by slow solvent evaporation. So using the typical method of depositing colloid on the substrate, letting solvent evaporate, and observing these nice superlattices from cubes. Some groups did, I think Sarah Balz did electron tomography, identifying some defects. And then Feldman group, for example, reported this interesting exciton delocalization. So and already this...
Could you say what is this Feldman group thing?
Yes, I'll talk about it. So already these early works started to report interesting optical effects. For example, shift in photoluminescence. It's a red shift. When you go from the solution of nanocrystals to the superlattice, you see that emission wavelength becomes longer in the superlattice as compared to the solution. And several explanations have been proposed for that. One was the environmental effect. So you change your dielectric constant. When you go from the solvent, a low dielectric constant, to the film, high dielectric constant. And that is known to affect exciton energy. Another explanation is self-absorption. Because the Stokes shift between absorption and emission is relatively small in perovskites, once you put a lot of nanocrystals close to each other, part of the emitted light will be reabsorbed and then re-emitted, and that would cause kind of filtering effect and artificially shift photoluminescence to the longer wavelength. Another explanation was the coalescence, so nanoparticles fuse together forming bulk-like particles with a smaller band gap, and that somehow contributes to the redshift. And then another explanation, for example, in that work, in that early work, was exciton delocalization. So it was proposed that in these superlattices, nanoparticles are so close that there is an overlap of the excitonic wave functions, and there is a formation of mini bands, and that's what causes a redshift. So the field progressed very rapidly from the start, and I'll just show this slide. You don't need to comprehend all of it, but it's basically tracking of different syntheses of high-quality perovskite nanocrystals, starting from the very first generation in 2015, all the way up to now. So meaning that there are, if one looks in the literature, one finds 7 or 8 different recipes of how to make high-quality perovskite nanocubes. And I think this is important as we start talking about cooperative effects, because each synthesis means a different surface passivation, different ligands, different growth conditions. So I'll be talking about these two generations today, the first one and the second one. So we started our work with this first generation of perovskite nanocubes, made by the method essentially developed by Kovalenko group in Zurich. So it involves reaction of solubilized lead bromide with cesium oleate. As a result, we form this about 10 nanometer edge nanocubes, which are passivated by allyl ammonium bromide and oleic acid or cesium oleate, which are in dynamic equilibrium. So this is one difference from, for example, lead sulfide to cadmium selenide particles, where ligands are much more tightly bound. With perovskites, since interactions are ionic, the ligand attach and detach in the solution. So the first superlattices we made were made by the solvent removal. So we dispersed nanoparticles in hexane, put them on top of the perfluorinated liquid, perfluorodecalin, which is an anti-solvent for nanocrystals, but is miscible with hexane. So hexane is slowly diffused into this perfluorinated liquid, producing these clusters of cubic particles, which then you can, for example, disperse in oleic acid and further characterize. So we performed some, let's say, study of topology of these objects to confirm that they are indeed three-dimensional superlattices. So you can deposit them on glass and take a profile, see that it's, for example, 5 by 5 cube. And by this method, one can grow pretty large superlattices, the supercrystals, with the dimensions like 50 by 70 by 50 microns, which contain 10 to the 11 nanocrystals. So, which is not surprising because I think a few days ago Michael showed example of lead sulfide supercrystals, which was even grown on a bigger scale. So now we looked at the smaller superlattices in electron microscope. So here's one example of this smaller superlattice in CM, and recorded wide-angle electron diffraction, and noticed something remarkable is that typically you would expect to see arcs, but we saw very, very narrow arcs, practically spots, indicating very high crystallinity of the superlattices.
Well, that means single crystal, no?
Yes, so it means essentially that each cube inside of this supercube is aligned with respect to each other quite precisely. And just to kind of calibrate you, here's an example for cadmium selenide nanocrystals, which also form a nice close-packed lattices. But then when you take wide-angle X-ray diffraction, you see that the arcs are typically much broader. In the low-angle diffraction, you see spots, as you would expect, but in wide-angle, you see that there is some disorder of nanocrystals with respect to each other. So we decided to study it with an X-ray diffraction, and in that case we shifted to solvent evaporation, so we can grow superlattices on the substrates kind of in this plain fashion, because by the previous method you form aggregates of superlattices and it's not convenient to study. So what we did, we used with the dispersions of perovskite nanocubes, either in toluene or in tetrachloroethylene. Tetrachloroethylene gives just empirically more reproducible results. So the way experiment works is that you take a petri dish about 5 centimeters in diameter, 1 centimeter tall. Inside we put 3 silicon substrate, 1 square centimeter area, and drop casted 30 microliters of solution onto each. Close the petri dish, leave the solvent to dry, and then depending on the concentration of particles, one can form this, let's say, isolated supercrystals or superlattice films, as we call them. For X-ray diffraction, there is really no difference between these two kinds of samples, but this shows some degree of control. Next, we recorded wide-angle X-ray diffraction measurement. So it's a very simple experiment in a typical diffractometer in chemistry labs. You put the sample, there's an incident beam, diffracted beam, and you scan it as a function of angle or use it to be detector. So what we saw is the following. So for the superlattice films, we saw some peaks in the low angle region, which one would expect because of the periodicity of cubes. And then we saw some unusual effects. For example, in the first Bragg peak, it had some fine structure. For reference, this is how similar diffraction experiment looks for disordered, randomly ordered, essentially powders of nanocrystals. You have all the Bragg peaks which one expects from the orthorhombic perovskite, which are broadened because of finite nanocrystal size. And in superlattice instead, first you have only few Bragg reflections due to preferred orientation. And then, moreover, there is some intensity modulation, as we call it. Again, to give a reference point, if one looks at the classical works from Bawendi group in the late 90s, so FCC cadmium selenide superlattices, here's a low angle electron diffraction, but then at the wide angle electron diffraction, what they saw in these materials is basically just an effect of preferred orientation, but no any additional modulation.
So I have a question.
Mm-hmm.
I mean, why do you have these 1, 1, and 2 peak disappear? How is that possible?
Because in the random sample, these nanocubes are oriented in all possible ways, so you see all crystal planes in the diffraction experiment.
So you have to rotate the X-ray to see.
Yes, yes.
Okay.
In this experiment, if we start rotating the superlattice with respect to the beam, then we start seeing other extinct reflections, yes.
So you have a single crystal, basically.
Yes, which has also preferred orientation with respect to the X-ray beam.
And it's wider is because there's a little bit of misalignment, or?
Yes, I think it's because there is a mosaicity.
Yeah.
So these supercrystals, they lie on in plane, but then they are rotated with respect to each other.
What about the two different lattice parameters you see in the first Bragg peak?
So, okay, yes, so this, I'll explain where this thing comes from. Because often, in the early works, this has been interpreted as a orthorhombic splitting to lattice constant. But if you do a simple sort of Bragg analysis, you will conclude that your particles should be like 100 nanometers to see two orthorhombic reflections. Well, in this case, this is a nanocrystal, so there is inconsistency. And the reason is that the origin of this structure is not, it's a superlattice origin, essentially. So, and what I mean by that is the following. So, the origin of this peak splitting arises from what's called the multi-layer diffraction effect, which has been first observed by Schuller, not first, but in the bimetallic superlattices grown by metal evaporation. It has been observed in the 80s. When you have alternating superlattices of two materials with different electron densities, you have a secondary interference, essentially, effect. And this is what we seeing in this Perovskite superlattices. So, so you just can apply a Bragg law. So another way to look at it, it works as a diffraction grating. And you see different orders of diffraction due to the superlattice. So you can plot it, well, you can analyze this split peak. So now I replotted it from 2 theta to the Q scale. You can fit positions of these peaks as a function of Q, and just using this Bragg equation determine the interparticle spacing.
And the stuff in between is all in the mean? Or?
Yes, so the stuff in between is the ligand. So it's oleolamine oleic acid mixture. So here it's the same peak replotted on a logarithmic scale, so we can better fit the peak position and also add background of some disordered nanocrystals. So now I take these red spots and just plot it Q versus N following this equation. I can fit it and obtain the lambda value of, for this particular sample, 12.2 nanometers. And then from TM of monolayers, we were getting a range of distances 11.5 to 12.6 nanometers, which is in a reasonable agreement. So that was our first analysis of this phenomenon.
Can you tell again what is the difference between the blue and the orange?
Just the density. So it's two different materials.
But in this case you have perovskite with two different densities.
So you have a perovskite nanocrystal, you have organic ligand in between, and then you have another perovskite nanocrystal ligand in between.
So that's the ligand in this case.
Yes, so it helps to create the contrast in electronic density that then produces this interference.
So 12.2 would be twice the oleic acid.
So 12.2 nanometers, it's a center-to-center distance between nanocubes. So if nanocubes are 10 nanometers, then 2.2 would be whatever is in between.
Is there a sense for how thick the ligand layer has to be to see this effect? What you see in front of you?
Yeah, so a single molecule is how thin the ligand layer should be.
In order to see this effect, yeah.
I think it can be basically much thinner or thicker. I don't have a number for the upper boundary. As long as there is no disorder, you would be able to see this effect. But disorder would kill it, and I'll show how exactly.
One more question. You see it in small angle in addition as a reflex, then probably, right?
Huh?
You see it in small angle.
Yes, yes, we do it also in a small angle. Yes. Because we focused on wide angle because that was something new about this case. So one application of this simple analysis is we can track effect of vacuum. So once we operate the solvent under ambient pressure, we put superlattices into diffractometer and we measure the diffraction pattern, and we see that the first Bragg peak has this green colored shape. Then we turn on the vacuum. It's a medium vacuum, so the oil pump, and keep recording diffraction patterns after some period of time. And we see that this pattern evolves. So what happens is that you remove the trapped solvent from your film, nanocrystals move closer, that changes interparticle distance, hence modifies your interference pattern, and then for each time point we can extract lambda and see that after about 80 minutes under vacuum, we contracted our superlattices by about 0.3 nanometers, which is consistent with the approximate size of tetrachloroethylene solvent molecule. So that was a simple interpretation of this result, but then it shows kind of what we liked about it is that it shows the power of this simple Bragg analysis.
Why is the curve sigmoidal in shape?
I mean, why it's not just smooth? Yeah, that I don't know why there is such a drastic jump over here.
But shouldn't it be sigmoidal? I mean, you're evaporating discrete small numbers of. I mean, if you say this is equivalent to the size of one molecule, I mean, it's a discrete effect, no?
Yeah, but it's a discrete effect, but it happens on a. I mean, in the experiment, you're looking at many superlattices on a substrate.
Oh, okay.
Your X-ray beam is fairly large, 2 by 5 millimeters. You're collecting macroscopic signal, and then if solvent, I mean, that here I think we need to think about the dynamics of solvent removal. Why it would happen?
Okay.
Like,
if you do a peak fitting analysis, does the peak breadth change as time goes on?
Say again?
Does the peak breadth change? So imagine if everything is uniform throughout and you're drying asymmetrically, so the top layers lose it first, whereas the bottom layers,
then it would...
that would change. I mean, that could give rise to weird non-linear effects. We could also expect a broadening of the peak.
Yeah, we haven't looked at that, because I mean, at the time, we were only able to do analysis just by looking at this lambda. So now we could also do more detailed analysis and determine, for instance, like disorder also. So doing this, if we go back and reanalyze this data, yes, I think we might see, for instance, because the top layers would go closer, perhaps more ordered, while the bottom will remain still wet and so.
How thick are these again? Like 50 microns or so?
The thickness. Yeah, it's no. I mean, it's not 50. It's I think more like 10 microns, 10 micron thick.
So, to see, one is that from here you conclude that you remove one layer of salt.
I mean, we see contraction that we interpreted as drying the superlattice effectively. Yes.
And then, can you tell how much solvent you have left?
No, that we cannot tell. We just see that nothing happens.
Could you reasonably conclude that there is no solvent left?
No, we could not. To do that, I mean, we would need to look, because when you talk about solvent, like here, the solvent is from which the self-assembly was performed, tetrachloroethylene. But then nanocrystals themselves came from the synthesis in a long-chain solvent, octadecane, which is also, we suspect, still present in the sample. So we think of solvents as different solvents. So here I cannot tell that all solvent is removed yet, because then I'll show the data when we start heating them up. So we subject them to vacuum and then we heat them up and we still see contraction, which might be further explained by the escaped solvent. So then what we did, we try to look at try to construct this physical picture of superlattice diffraction and try to push it a step further. So to explain it in this schematic way, so in a nanocrystal superlattice you have these cubes, the green cubes, and each cube itself is a crystal. And it consists of crystalline planes separated by d lattice constant. For perovskite it would be orthorhombic lattice constant. Then there is a secondary lattice constant, the superlattice constant, lambda. So when X-rays fall on the sample, first each nanocrystal contributes a Bragg peak at the position of lattice constant with the broadening because of the finite crystal effect. And then there is an additional phase shift due to the superlattice periodicity, which shows up as this diffraction grating, if you will. And then two effects combine and give this superstructure of the first Bragg peak. So the next, now this thing has been known again in epitaxial superlattices of 3-5 semiconductors and metal films. So in the 80s, by metal sputtering, people were making all kinds of like tungsten, copper, multi-layers for applications in high-density magnetic recording, and they observed this effect. They developed a numerical model that we adopted in order to now quantitatively fit the experimental patterns. So, and I'll just show it, I won't show any equations because they're all in the studies, but I'll show the effects of each parameters. There are 5 parameters in the model. So first is that we represent a nanocrystal as a set of diffracting planes. So each nanocrystal has a size, means there will be n number of planes separated by interplanar distance. So, and each of these nanocrystals will give a diffraction peak, which would be broad because of finite size, and would be located at a certain Q position because of the specific D. Next, when you stack them in the ideal case, without any disorder, you have interference due to this periodicity, which is then combines with this profile shape and gives you this sharp periodic peaks. But that's not what we see. We see them much broader. And this is where the disorder starts playing a role. Now we add on top of this, we introduce a normal distribution of disorder in nanocrystal positions, basically a very small variation in phase shifts, which then broadens the calculated signal, but lets us to obtain, numerically fit the value of interparticle distance, and more importantly, its fluctuation. And then lastly, because there is a size distribution of nanocrystals, we can calculate it we can represent our sample as consisting of multiple size pure superlattices, just to simplify the model and the calculation, and then add this effect on top, and also determine the average number of planes in a nanocrystal and its standard deviation. So we can perform this all in Python, and now for a given sample of perovskite nanocubes, we can quantify average size of nanoparticles, 13 planes plus minus 1.5, interparticle separation and its fluctuation, and then back calculate the superlattice constant. So why is it useful? One illustration, now we start heating these superlattices. So we first vacuum them to make sure sample is stable, at least that there is no obviously trapped solvent. Then we start heating it, keeping it for 15 minutes at each of these temperature set points, and see what happens with this Bragg peak, how it evolves. So it obviously evolves, becoming more sharper and changes the structure. So by applying the model, we can obtain the following picture of the changes. First, since we can fit D, we can see that the lattice constant of nanocrystals is expanding as we heat in the sample, which is consistent with expectation. Because perovskite nanocrystals, at room temperature, when they are big, about 10 nanometers, they are orthorhombic. As you start heating them, they change their structure to tetragonal, eventually becoming cubic. So lattice constant expands. We can see this and then compare with literature with a consistent result.
So just in your tetragonal region, you still have the orthorhombic line. I'm not quite sure what's going on there.
So here, I mean, the way we compare it with the literature is that, I mean, from our model, we only obtain one lattice parameter, and we don't know which one it is, A, B, or C. So we calculate sort of an average cubic-like constant, which then we plot. These values, AC for the tetragonal, orthorhombic, and cubic, are taken from the Kanazidis work on a single crystal perovskite, on a single crystal cesium lead bromide 3, where structure is unambiguous and fully resolved as a function of temperature.
So, one question, do you develop a dipole and the orthorhombic?
That we don't know. A dipole in the orthorhombic structure?
Yes, or the travel.
That we don't know. That we cannot. I mean, we haven't studied this. But people do study ferroelectric domains in perovskite, microcrystals, nanocrystals, and this is a
That
possibility.
would also affect the lattice constant. Yeah.
As you heat it.
Well, you change the structure. Yeah.
I mean,
True. Another contribution that would.
Really?
Is this reversible?
So this is what so when we did this runs, we went to 250 degrees and just saw the whole coalescence balkanization. So that unfortunately I don't know. We didn't do like hysteresis type studies.
I'm curious because if they come back to the solvent evaporation.
Yeah, I mean, hearing that those discussions made me think that that's would be very interesting to do, to heat it up, especially because other thing which we found out is that as you heat it, it contracts by about 2 angstroms on average, and then the order of superlattice improves as you heat it. So the disorder decreases. And then seeing if we go from 125 back to room temperature to see if it gets disordered or if it stays more ordered, that would be an interesting thing to do, which we haven't thought of at the time.
Your solvent here is still the tetrachloroethene?
Yes, yes.
And what's the boiling point of that?
120 degrees.
So that's a little before where you again see a jump. So it's not a continuous transition from orthorhombic to tetragonal to cubic. There's a jump at about 135 degrees Celsius.
Yeah, so here for nanocrystals this transition is suppressed, so it happens at a lower temperature than for bulk. But yeah, this I mean the combination of these effects, with this approach we were not able to disentangle.
What is your temperature ramping rate?
So it was, I think it was 5 degrees a minute. So it was.
So it should be basically at equilibrium at each data point.
Yes, yes. Because then what we do, we reach the set point and then we sit for 15 minutes on it and record the patterns. And why we sit for 15 minutes? Because in the preparatory experiments we collected it more often to see when sample stops changing. So we did it. We tried to do it kind of.
Sorry to get more technical here, but is this synchrotron radiation?
No, this is
okay,
just.
So there's no chance of X-ray damage.
So even on the laboratory instrument, there is an X-ray damage if you keep recording patterns over and over. So in this case, I think it's minimal because we use a 2D detector. So acquisition, so to acquire one pattern takes literally a few minutes. So, but when we expose it for like hours, because we did it in some experiment, we would see the intensity decrease and beam damage. Yes.
Another question.
Yeah.
I mean, you have this tetragonal low symmetry structure at low temperature. Is the crystal, are they aligned? Like
So
the tetragonal defines a symmetry lower than the cubic symmetry.
So here one notice that this is the symmetry of structure of nanocrystal,
that's what I
not
mean.
the superlattice. Okay.
Is the structure of one nanocrystal
One
related to the next one next to it, or are they sort of oriented randomly in 3 possible?
No, they are okay. We think they are all oriented in the same way because that's why we keep seeing this effect. But
your data on in B here suggests that you see just an average lattice constant. That would suggest that it's maybe not aligned, would it?
so, I mean, you would expect lattice constant expansion of a perovskite as you heat it up, regardless.
Sure.
Right, so what you're asking, if I understand right, whether it introduces additional misorientation or
Well,
not.
if there is coherence between the tetragonal symmetry of one nanocrystal and one next to it, or if it's, I mean, we've seen was it on Wednesday? We've seen that in Michael Grunwald's talk that there's this crystal where you have different discrete, like these discrete rotator crystals. And maybe that's good.
I don't think, I think you're asking about precision, which I don't have an answer for.
Well,
Yes.
you could get that from the 2D data, because if the more orientational mismatch you have, the broader your arcs are going to be.
Right.
So if you go back to the 2D data, you should see that if they are sort of coalescing, the arcs will get narrower and narrower and narrower.
Right. Okay.
So that should be pretty easy to check.
Okay.
I would expect the fact that you see this at all indicates that they're probably pretty well aligned to begin with, and you're just sort of gradually aligning a little bit more. But you go back to the 2D data, and it'll show you pretty easily.
Okay, that's a good suggestion. Yes. Okay, so then we extended this to the nanoplatelets because you can grow this very nice 2 monolayer nanoplatelets and form, again, large films that are iridescent. We applied this method because with nanoplatelets now, if with nanocubes you treat you treat a nanocrystal as a sort of impersonal scattering planes. With the nanoplatelets, which are much thinner, now you can assign, let's say, atomic scattering factor to each plane, and that helped us to, for example, refine the surface passivation of nanoplatelets. So we found that this nanoplatelets passivated with ammonium, with allyl ammonium molecules, and with only like 73% surface coverage, and they have a distorted crystal structure. So that's.
What's the shape of these nanoplatelets?
So these nanoplatelets are quite irregular. So they are large, they are very uniform in their thickness, but then the dimensions can be 100 by 100 nanometers. So they're essentially sheets, colloidal sheets, which then pack very nicely face to face, and then give.
So the thickness is one.
Two monolayers, so 2 octahedra.
Okay.
So it's 2 octahedra with the cesium in between, and on the surface they passivated, in our case, with allyl ammonium molecules.
That does bring up an interesting question for what you showed in the previous slides, though, is that with the cubes, what's the size dispersity?
So size dispersity from TM, what we can see always in our, let's say, best samples, it's average size 10 nanometers plus minus 1 nanometer. That's what we get from TM.
So that's on order of your ligand shell thickness. And so I'm wondering, what role does that play in terms of this densification? Because as it's densifying, you're basically going from something that has a little bit of a fuzzy layer that can sort of accommodate any deviations in dispersity to less and less ability to accommodate that. Have you looked at these under TEM afterwards to see if there's any shape change in the particles or any sort of redistribution or crack formation in the crystals, things like that?
No, we haven't looked at TM. I mean, after heating, you mean?
After any treatment, but yeah, especially after heating.
I mean, no, after heating, we haven't looked at them because, I mean, they are too thick for TM, and on a small superlattices, we haven't done this. I think, yes, we haven't done it.
It'd be interesting to know how it's accommodating if you have a 9 nanometer and an 11 nanometer next to each other, and you have this like 2 nanometer soft sort of component between them, they can compensate. But if you're condensing them further and further, at some point the strain of that is going to disorder it rather than order it.
So in fact, when you look at monolayer in TM, which is the easiest thing to do, you see that sometimes if the cube is a little larger, it still kind of fits into the monolayer. But what happens with it once you do it on a superlattice scale, that I don't know. So to wrap up this part, what we achieved here and what we learned about this material is that it's very well ordered, and then we developed these techniques for superlattices of cubes and nanoplatelets with the code and raw data basically available as part of supporting information. So now I know Bawendi group recently used it for synchrotron experiments on nanoplatelets as a function of temperature. Also, I think Talapin group used it to characterize changes in nanocube superlattices after ILD. So yes, two people who do theory and simulate dynamics of superlattice formation. If you start making your codes available, then experiments might start also trying to use them for their systems, and that maybe will accelerate the progress. Okay, so here I want to start talking about collective optical properties, and I will return to this picture again. So we established this diffraction effect. Now the question is, what if you excite these are semiconductor nanocrystals, they are light emitters, right? So they have a band gap, so if you excite them, and they will all emit light, then something similar should happen like with X-rays. So you can think of each nanocrystal as a, let's say, simple oscillator, which oscillates at with this amplitude A1, frequency omega 1, with some phase phi 1. Then you can write it out for n nanocrystals. Then if they are all the same, meaning that there is no size distribution, no all this reality, let's say, then the frequency is identical, amplitudes are identical, there is no phase shift, and what will happen to the collective amplitude is that you will just add them up, and the intensity in this case, because what you measure is the intensity of the emitted electric field, you would obtain this form which scales as n squared, right? So this is basically the crux of the physics of superfluorescence. So I don't know if it's these thoughts or the some other thoughts which inspired Dicke in '54 to develop a theory of coherence in spontaneous light emission, which became known as Dicke Superradiance. So at the time, there was a lot of studies in nuclear magnetic resonance, so Dicke naturally thought about protons being in the, excited by the radio waves. So, and that's basically the process he proposed, is that you have a ensemble of degenerate two-level systems. So they're all identical, there are no multiplicity of states, just two-level systems. They are confined within the volume of lambda cubed, or the length scale within which they confine is not much larger than lambda. Then you excite them all together, and after some time they produce this superradiant pulse with a peak intensity proportional to the square of the number of emitters. So this effect became known as superradiance. So that was treated theoretically in this paper, both quantum mechanically, semi-classically. And then the first experiment came in '72. It was done with a hydrogen fluoride gas at room temperature at MIT, a Feld group. So they used this cylindrical cell with a low density, with a low pressure of hydrogen fluoride, 1.3 millitorr, or 10 to the 13 per inverse centimeter cube. So basically it's 40 molecules per every cubic micrometer. So the collisional times are very long, meaning that once you excite the molecule, the coherence of this excitation persists for a very long time. Moreover, they studied not an electronic transition, but a rotational transition. So they excited the molecule to the first vibrational state, and the superradiant transition was observed in this between the rotational state, which means that the wavelength was very long. We're talking about tens of micrometers wavelength. So 84 micrometers. And that's what they saw. They saw in the time-resolved experiment. So after excitation, they saw that after some time delay, the gas produces very bright pulse of light, which kind of decays in this oscillatory manner. They measured the peak intensity versus squared pressure. So meaning that, let's say you can think of it as n squared on the x-axis. And you saw that indeed the intensity of this peak scaled as the n squared, as one would expect. So they said that this is a Dicke superradiance. They proposed this picture that later became also quite influential and propagated to many reviews and books. So you excite your sample with a fast excitation pulse. Then if it's a simple spontaneous emission, it decays on a certain time scale, and intensity distribution around the sample is isotropic because each molecule emits light independently. In case of superradiance, it's a directed emission. So in this case, in the direction of the cell, direction of the most number of emitters, because there should be some phase matching. And then it's a very short pulse of light. So next, in '75, two theories from Italy, Bonifacio and Lugiato, said that, wait a second, it's not Dicke superradiance. Actually, what you saw were superfluorescence. And what was the difference? The difference was that they added this step of build-up of coherence. So they say, okay, what happened is that you excited your molecules, but at the beginning there was no coherence. Each excited molecule needed some time to couple to the field and then essentially perform a phase transition into the macroscopic coherent state, from which then the emission happened. So they added this step, also treated it for inhomogeneous broadening, and then called it superfluorescence. So this is where I believe superfluorescence actually starts taking its name. Next experiment was in the gas of sodium vapor, 1976, group of Serge Haroche, who got the Nobel Prize recently. So in this case, they again had an elongated cell, gas of sodium atoms, pumped it with 2 pulses to this 5s state, and then observed again a delay emission of light, which is varied with the excitation intensity. So higher excitation intensity, faster superfluorescent, lower excitation intensity, slower superfluorescence. They did it for the two transitions, plotted variation of the decay time versus excitation intensity. Here it's inverse. And then again, intensity versus excitation intensity squared, linear trend as one would expect for the Dicke case. Here's more recent experiments with rubidium vapor. So this is a confusing plot, but basically, I think, let's see, in this paper, the researchers basically show the picture of the experimental setup, so sort of what it takes to get it in the atomic vapor, some pictures of the superfluorescence, and then superfluorescent pulse as a function of excitation power. So at a weak excitation power, there is a large delay. So this is this red axis. That's why it's a weird plot. At a high excitation power, n is much larger, superfluorescence happens faster and shows this oscillation. So now, going to perovskites, in 2018, the Kovalenko group published this remarkable paper in Nature, where in the well-ordered lattices of cesium lead bromide of the first generation, so if you remember back to the slide with the long synthesis I showed, this was size selected particles from the first generation. So what they saw is two features in the optical spectra at low temperature, the narrow intense feature attributed to superfluorescence. They saw, as a function of time and excitation density, they saw the oscillations, plotted signal intensity, for example, versus excitation density, and saw that it's proportional to n to the 1.5, not quite 2, but still superlinear. And then saw shortening of the delay time, so time between this peak and 0, as a function of excitation fluence, which also sort of fit together into this phenomenon. So again, this is I think remarkable, and one of the case studies which basically was a big motivation for this workshop, where structure property correlates together. And other remarkable thing is that in the previous examples, you always need to go to exotic systems like molecules or atomic gas, while here it's something you make in a fume hood, grow on a substrate, but then you have to, cool it down, but still quite a remarkable advance. So in our efforts, at that time we developed, in Mana group where I was, the new synthesis of nanocubes was developed that now produced very uniform nanocubes with a very sharp excitonic peaks by replacing olyilamine with a secondary amine, because olyilamine was binding strongly and contributing to dispersity of shapes. So we decided to work with these nanoparticles in our experiments, and then we were looking for cooperative emission in these superlattices. So we cooled it down to 4 kelvins, saw a single peak, and tried to do intensity studies. The only thing we saw is that when we increase excitation intensity, the photoluminescence broadens, shifts a little bit, but then when you return back, then you see that the superlattices essentially has been fried. So we couldn't find any signatures of cooperativity here from this simple measurements. However, what we noticed is that when you keep the superlattices at room temperature, over time the lower energy peak starts growing by itself, which was surprising. So we looked at the same superlattice 7 days later. So experiments were done at 4 Kelvin, but in between it was kept at room temperature. And what we saw is that after 7 days on its own, sample changed, forming this intense low energy peak.
This is superfluorescence.
We don't know. So we try to measure it as a function of power. Again, in this case, sample was more stable, and the explanation for this peak, which we came up with, was unfortunately more trivial. So we saw that what happens is that nanoparticles start coalescing inside the superlattice over those days. And then what you have is that after a week, you essentially have a mixture of small superlattices with large band gaps and small nanocrystals with large band gaps and large nanocrystals with small band gaps. There is energy transfer going on, and that's why you have this secondary emission. And this is one of these key differences between, I think our choice of the sample synthesis and the different surface passivation resulted in these effects, not the ones which, for example, other groups saw. However, there are two instances when I think, I don't know if we saw superfluorescence, but we might have. So the possible superfluorescence case one is that when we leave this superlattices on air, what happens is that small nanocubes form bigger and brighter particles. And in this case, you have a double peak emission with an accelerated photoluminescence decay. Moreover, when you look at these bigger particles on their own, as a function of excitation fluence, you see that in the time decay plots, there are these interesting oscillations that might be interpreted as superfluorescent or perhaps some other effects. The second case, so we reverted back to the nanocubes made by the first generation synthesis. I think the most similar to the ones which were originally reported from in 2018. And in this case, we actually saw at low temperature appearance of additional resonance. So I believe we reproduced the observation from 2018 paper. For this sample had to be kept in vacuum for essentially 3 months. But these particles, for instance, did not show any signs of coalescence into bulk material. So there is some coarsening happened, perhaps which brought cubes together in some local domains, which then resulted in the appearance of this new resonance. And when we studied the strength of this, let's say, resonance versus the excitation fluence, we saw that for some range, there is a superlinear power dependence with exponent around 1.4. In the 2018 study, it was 1.5. So we think in this case, we might have, we see a similar effect. So here, to conclude, I return to these two questions. First, what makes superlattices of perovskite special? It's their very good crystallinity as compared to other particles. Perhaps maybe it's something that should have been anticipated, since they are cubes, not spheres, so there is not much rotational degrees of freedom, but it's indeed quite an exciting material from this point of view. And then to answer the second question, as always, there is, I think, more work to be done to understand how the surface chemistry, the quantum yield, and the structure of the superlattice contributes to emergence of these cooperative effects. And I think this is an excellent example where where you really need chemists, physicists, and theorists, both of electronic structure and self-assembly, kind of come together to tackle the problem. So with that, thank you for your attention, and I'll be happy to take more questions or continue the discussion.